Yes, sir. Thank you very much, sir. Uh, a very good evening to one and all present here. Am I audible, sir?
Yes.
A very good evening to one and all present here. Being the head of the mechanical department, I feel a very great pleasure to introduce today's eminent personality with us for this program. So for today's, we are having chief guest and speaker, Dr. Rajendra B. Wagurde, sir. Sir has done his doctorate in physics from North Maharashtra University. Sir has 27 years of teaching experience and currently working as principal in DNC BPS Shirish Madhukar Rao College, Jalgaon. Again, more than 30 papers he have published in international and national journals. Sir is also a member of Academic Council at KBC NMU. Sir also worked as a member of faculty for science and technology at KBC NMU. Sir has won many awards from the renowned platform like Vidya Ratna Puraskar from Indian NetSet Association in 2010, then Dr. Homi Bhabha National Award in 2011, and Academic Leadership Award in 2019, and many more. There are many more things to tell about our today's eminent personality, that is our chief guest, Dr. R.B. Wagurde, sir. But due to the limited time span, now directly I would like to invite today's eminent speaker, Dr. R.B. Wagurde, sir, for this session. Please, sir.
Good evening to all. Am I audible to all of you?
Yes.
Yes, yes. A good evening to all of you. I am very happy to see that the Godavari College of Engineering and Polytechnic Jalgaon establishes a material advantage Godavari Engineering chapter with association of ASM International, and today I am going to discuss the topic nanomaterials synthesis and applications as a first lecture in this chapter. First, I am very thankful to Dr. Ullaji Patil and Dr. Vasha Patil, President and Secretary of Godavari Foundation, for giving a permission to establish this chapter in a Godavari Engineering College. And my inspiration, Godavari Patil, who is my grandmother, she is always inspiration for me, and I am very thankful, and I am very inspired by Mr. Sudhakar Bonde, who is the chairman. He talked with me and asked me to talk about this. There are many eminent persons, and your lecture should be a very good lecture. Therefore, thank you for Sudhakar Bondeji for providing me this platform. Sandeep Parekeji, Secretary, Dr. V.H. Patil, Principal of the Engineering College, all the organizing committee members, and all dignitaries from renowned institutes like IIT and other renowned institutes. Today's my topic of discussion is a nanomaterials synthesis and its applications. These are the contents of my today's talk. The first, since in this chapter we have students enrolled, basically I am covering the basic concepts of nanomaterials. For the eminent persons present over here, they may know all about these things, but this presentation is prepared by focusing on the student members. What are nanomaterials? Nano means small, very small. Actually, nano, it is a unit of length in metric system, and it is equals to 10 raised to 9, 10 raised to minus 9 meter. ISO defines nanomaterials as a material with any external dimension in a nanoscale. That is the scale ranging in between 1 to 100 nanometers, or having internal structure or surface structure in a nanoscale. Now, this is a figure. This figure shows some things existing in nature having a different physical size, Here, this is a scale. On this scale, you can see different things having their physical size. And here, you can see a nanomaterials, examples of nanomaterials within a range of 1 to 100 nanometers. Now here, you can see liposomes. It is an example of nanomaterial. What is this liposome? It is a spherical shaped vesicle, that is a tiny bubble. And it is composed of one or more phospholipid bilayers, and it resembles the structure of cell membrane. It is a one example of nanomaterial. The another example is fluorescence. It is allotrope of carbon atoms connected by single or double bond to form a closed mesh. Then you can have a dendrimer. It is highly ordered branch polymeric molecules. You have a carbon nanotubes, the most famous nanomaterial. It is the strongest, it is the strongest and stiffest material yet discovered in terms of tensile strength and elastic modules. These are the allotropes of carbon with nanostructure. Hello?
Yeah, it's okay now.
Yes, yes. Drug delivery. All these nanomaterials, they are used in different applications like drug delivery, tumor research, radiation therapy, sensors, and some of the materials, they are used as additives for various structural materials for electronics, optics, plastics. पुढे जात नाही का? One minute. Yes, yes. So whatever the nanomaterials, these nanomaterials can available in three forms: naturally occurring nanomaterials, unintentionally, that is incidentally generated nanomaterials, and engineered nanomaterials. For example, volcanic ash, soot from forest fire are the naturally occurring nanomaterials. The incidentally or unintentionally nanomaterials are the byproducts of combustion process. For example, welding, diesel engine produced. These are ultrafine, chemically heterogeneous particles. And important thing is engineered nanomaterials. We are interested in engineered nanomaterials. These engineered nanomaterials are intentionally produced and designed with physicochemical properties for specific purpose or the functions. Now, when you talk about the nanomaterials, the dimensionality of nanomaterials is very important. These nanomaterials can be classified as 0 dimension, 1 dimension, 2 dimension, and 3 dimension nanomaterials. This dimensionality plays a major role in determining the characteristics of nanomaterials, including the physical property, chemical property, electrical property, biological property, and etc. With the decrease in dimensionality, an increase in surface to volume ratio is observed. This surface to volume ratio is very important. We have to control it using different processes during synthesis. And this dimensionality, this indicates that smaller dimensional nanomaterials have a higher surface area compared to 3-dimensional nanomaterials. Recently, 2-dimensional nanomaterials are extensively investigated for electronic, biomedical, drug delivery, and biosensor applications. Here are some examples of materials according to the dimensionality. Here we have two types of nanomaterials, isotropic and anisotropic. These zero-dimensional materials are isotropic. They are called isotropic because properties of such a materials are identical in all directions and they are available in spheres and clusters. The anisotropic materials, their properties depends on the direction. For example, if you consider wood, in a piece of wood, you can see a line going in one direction and this direction is referred as with the grain. Similarly, in anti-isotropic, some properties are aligned with in some specific directions. And we have nanorods and nanowires as a one-dimensional nanomaterial, nanofilms, plates as a two-dimensional, and nanoparticles three-dimensional. Now here, how you can synthesis these nanomaterials? Because we want to intentionally produce nanomaterials in laboratory for some specific applications. There are two approaches. One is a top-down approach and another is a bottom-up approach. Actually, these nanomaterials are known in ancient days also. But since at that time, the characterization techniques are not available and therefore it is very difficult to characterize these materials. The top-down approach process, in top-down approach process, the bulk materials are broken into nano-sized particles. For example, mechanical grinding using mortar pestle. We know that in our country, in ancient days, the Rishi Munis, they prepare a medicine. While preparing a medicine, they use a mortar and pestle. And using the mortar and pestle, they prepare a fine powder of medicine. That is, they are preparing a small molecules or atoms of the medicine, and that may be in terms of the nano. And the another approach is the bottom-up approach. In this process, the nanoparticles are produced by building of atoms by atoms. An example is a molecular beam epitaxy. Nowadays, there are a lot of different methods available for synthesis of nanomaterials. Here, there is a list of many more methods: co-precipitation method, hydrothermal synthesis method, inert gas condensation method, and so on. Sol-gel method, spray pyrolysis method, biological synthesis called green synthesis methods. Using all these methods, you can synthesize nanomaterials. Now I am going to show you some of the nanomaterials which are synthesized in our college laboratory. Since I am working as a research scholar in KBC North Maharashtra University under the guidance of Pro Vice Chancellor Professor P.P. Patil, in the year 2006, we have synthesis nano cadmium oxide using co-precipitation method. And this is a transmission electron micrograph with its electron diffraction pattern. And the size we obtained is 12.7 nanometer and we obtain the spheres. That is a zero-dimensional material. We use this synthesized CDO for sensor application. And later on, nowadays, we are using a hydrothermal method for synthesis. And in our laboratory, we have synthesized these nanorod, nanoflowers of Fe2O3. Now, one important thing, during a synthesis, there are different parameters you have to control to obtain a desired structure. You may see that here, by changing a reaction time, here reaction time is 2 hours, reaction time is 4 hours, and reaction time is 6 hours. We obtain somewhat different morphology, not exactly morphology, but their size may get changed. Also, you can change the morphology by controlling different parameters during the synthesis process. In a hydrothermal, you can change the concentration, molarity concentration, pressure, you can change the temperature. All these factor affects the morphology of the produced powder. Now, this is a synthesis of nano composites. We have synthesized Fe2O3 with some polymers. All this, I am very happy to share that here there are some renowned personalities from IIT. All these characterizations are done in IIT IIT Powai, and they have provided us the facility of this characterization. Now this is a setup of hydrothermal. Here we have a Teflon autoclave, and this is stainless steel, and we have designed a PID controller in our laboratory itself. And using this Teflon autoclave and using this PID controller, we have synthesized nano materials in our laboratory. Now we go to the next thing, that is a technology. Technology, what is the technology? It is the making, usage and knowledge of tools, machines and techniques in order to solve problems to perform a specific function. Now here, what is a nanotechnology? When you talk about nanomaterials, you must talk about a nanotechnology, because after synthesizing nanomaterials, we should have its applications. You have to use some technology, and therefore we must know what is a nanotechnology. It is a branch of technology that deals with dimensions and tolerance of less than 100 nanometers. Nanotechnology is the study of manipulating matter on an atomic scales, and these are different definitions of a nanotechnology. So what is the origin of nanotechnology? The first ever concept was presented in 1959. Dr. Richard Feynman, the professor of physics, first time used this word nanotechnology, and then it is a coined by a scientist Nori Taniguchi in 1974. These are some examples which show how a small is a nano. I have already discussed these things. Now, why this nano word becomes a buzzword? Why people are attracted toward this nanotechnology? Because of these some reasons: faster, lighter, cheaper, can get into small spaces, energy efficient, develop unique properties at small scales. We'll see all these things in next slides, but these are some properties why the small objects are referred and why nanotechnology becomes so popular in the scientists in the world of material science. Same thing, why? The most important thing is that using a nanomaterials, you can control the physical properties, mechanical properties, optical properties, and electrical properties. These properties can be changed for desired applications with the synthesis, proper synthesis of nanomaterials. And according to our application, we can develop the nanomaterials, and therefore a nano is so popular. These are some applications of nanotechnology. Now, I think there is no area in a human being life where nanotechnology is not applicable. In every aspect of human life, a nanotechnology is useful. Now, here I am going to discuss nanotechnology in green energy. That is nowadays one of the very important application of nanotechnology. What is the green nanotechnology? It refers to the use of nanotechnology to enhance the environmental and sustainability to process producing negative externalities. We know that there are side effects of many synthesis processes, many processes, and basically this green nanotechnology is used to reduce these negative externalities. This green technology has been described as a development of clean technology to minimize potential environmental and human health risks associated with manufacture and use of nanotechnology products, and to encourage replacement of existing products with new products that are more environmental friendly through their life cycle. It also refers to the use of products nanotechnology. It enhances sustainability. It includes making green nanoproducts and using nanoproducts in support of sustainability. So why? By applying the green technology, what are the uses? It reduces the uses of non-renewable sources, reduces energy usage, lifetime and property value, and it increases the human quality in life. We will see all these things in applications. So green energy introduction. It is energy resources that are renewable, can be naturally replenished, fill something up again, clean, safe, and not harmful to environment. And these are some advantages and disadvantages of green energy. Advantages are negative impact to environment is zero, make pollution free environment, green energy solutions, good to everybody, easy to stabilize, more efficient. Only disadvantage is that it is costly to stabilize. Now, how you can use a nanotechnology in renewable energy? These are some definitions of what is a renewable energy. Why renewable energy we can use? We are interested in nanotechnology, use of nanotechnology. That's why I'm skipping some of the slides. These are some renewable sources: solar energy, wind energy, hydropower, heat energy, biomass. There are many sources of renewable energy, but all of them except geothermal energy are more or less directly related to the sun, and it is an abundant source of energy. It is a main source of clean and sustainable energy for the earth. Now, how you can use the nanomaterials in a green energy or in renewable energy? In a solar cells, in initial days, a bulk silicon is converted into discrete nano-sized particles. And these particles, they show distinct colors depending upon their sizes. For example, if you have film of 1 nanometer, it shows a blue fluorescence. If you have thin film of size 2.80 nanometer, it shows red fluorescence. And they produces a large voltage enhancement with improved power performance. But as there is an advancement of technology, there is an advancement in use of nanotechnology in solar cells. Extensively, we use the nanotechnology in increasing the efficiency of solar cells by using nano-sized particles, carbon nanotubes, and semiconductor quantum dots. So we'll see one by one. Nano solar cells. How can nanotechnology improve solar cells? Using a nanomaterials in a solar cell reduces a manufacturing cost, reduces installation cost, making solar cells ultra thin, reduces their material cost. Now, carbon nanotubes. Now, titanium oxide nanoparticle based solar cells are most widely used. They provide the carbon nanotubes. They provide a direct route, that is, the escape route to the electrons moving toward electrodes. Now, here in solar cell, we know that the current is generated by creating electron and hole pair. When a photon from sun energy bombards on the solar cell, it creates electron hole pair. And using a carbon nanotubes, you can have a direct route for flow of that. Now, similar to carbon nanotubes, you can use semiconductor quantum dots, QDs. These are the tiny semiconductor crystals. Semiconductor quantum dots are tiny semiconductor crystals. They have the potential to convert high energy photons present in the incident light into multiple electrons. Usually, this quantum dot produces 3 electrons when every photon of sunlight hits the dots, and therefore it increases the efficiency of your solar cell. The quantum dots are semiconducting particles that have been reduced below the size of the excitation bore radius, and these electrons energizes that can exist within them become finite. These quantum dots have been referred to as artificial atoms. Their energy levels are tunable by changing their size, which in turn define the band gap. This band gap is a very important factor in fabrication of solar cells. whenever we consider any oxide material or any material for fabrication of solar cell, first you have to consider a band gap. And using this band gap, we can have a different excitation energies, and the dots can be grown over a range of sizes, allowing them to express a variety of band gap without changing the underlying material. That means you can change the band gap, and the ability to tune the band gap makes quantum dots desirable for solar cell. Now we know that the sun's photon distribution spectrum, the maximum solar conversion efficiency occurs in material with a band gap of 1.34 electron volt. However, materials with lower band gaps will be better suited to generate electricity from lower energy photons and vice versa. If we have a single junction implementations using PBS, lead sulfide colloidal quantum dots, they have band gap that can be tuned into the far infrared frequencies that are typically difficult to achieve with traditional solar cells. That means with the help of this nanotechnology, we can have quantum dots and you can tune the energy. Half of the solar energy reaching to the earth is in infrared, most in the near infrared region. A quantum dot solar cell makes infrared energy as accessible as any other. The quantum dot solar cell that uses quantum dots as a captivating photovoltaic material. It is used to replace bulky materials such as silicon or copper indium, gallium selenide. Because the band gap of quantum dots can be adjusted, quantum dots are desirable for solar cell. Now this is another thing, gradient multilayer nanofilm, GML. It is an assembly of quantum dot layers with dots in gradient of nanoparticle size, composition or density. Properties of such nanostructure are finding its applications in designing of solar cells and energy storage devices. The GML nanostructure can be embedded in organic materials polymers like purine, polypyrrole, or can include quantum dots made of two or more types of materials. And this is one structure, it's a schema of GML nanofilm. The GML nanofilm, only 100 nanometer thick, can absorb the entire sun spectrum, that is from 0.3 to 2.0 electron volt. At the same time, gradient of the quantum dot size can create a gradient of electrochemical potential acting as an equivalent of built-in electric field inside a nanofilm. And this enhances transport of electrons and holes and improves internal quantum efficiency and photocurrent. Similar to GML quantum dots, we have a dye-sensitized, that is nano solar cell. These are the relatively inexpensive, made in non-vacuum setting, mainly at room temperature, relatively simple manufacturing process. They need a little thin layer chromatography. These dye-sensitizing solar cells are thin, lightweight, flexible, and takes approximately 3 months to produce energy saving if you want to cost of production. Here also you can use the nanomaterials. Now similar to solar cell, we have another type of renewable energy, that is a wind energy.
Not hearing anything. Is everything okay?
Are the 1 minute? 1 minute, please. 1 minute. What are the issues related to wind turbines? These are the distribution problem. Share, no? Was disabled. Hello, sir. Have you disabled me? Hello, hello, hello,
Hello.
sir. Have you disabled my screen sharing?
Just try it again.
Sir, I have a message. Host disabled participant screen sharing.
Co-host screen sharing only is allowed. So I have made both your things as co-host. Now please try.
Okay. Now, these are some issues regarding wind turbines, distribution problem, variation in wind speed, power control, life, weight, power losses, and efficiency. You can use a nanotechnology in wind turbine. The nanocomposite materials with excellent strength to weight and stiffness to weight ratio enable construction of longer and more robust blades. Low friction coating and nano lubricants provide means to reduce energy losses in gearboxes and thus further increase efficiency. The carbon nanotubes develops to make blades stronger and lighter, improving energy efficiency, and nano paints used to increase wind turbines lifetime. Now, these are some of the problems in wind turbine, and these are solutions with the nanotechnology. So, bioenergy. It is another renewable energy. Bioenergy, biomass is any organic material, may include wood, wood waste, straw, manure, sugar, sugarcane, and many other byproducts from a variety of agriculture processes. Some of this is burned to make electricity, some is made into biogas, biofuels like ethanol, and as a replacement of gasoline. Now, this is a flow chart how biomass energy is converted, but how you can use a nanotechnology to turn algae into biofuels. Algae carbohydrates can be converted into ethanol or they may be gasified into biogas. However, they pose various challenges. Such challenges can be met with nanotechnology. Algae have been successfully turned into biomass with the help of incorporation of nanocatalysts. The main applications of nanocatalyst in water purification, fuel cell, energy storage, biodiesel productions, in medicine, in dye, applications in carbon nanotubes, and several other point of applications. What are these nanocatalysts? These are the heterogeneous catalysts that are fragmented into metal nanoparticles so as to speed up the catalytic process. They have an increased surface area. They can be easily separated and recycled. And using these nanocatalysts in biomass, we can increase the efficiency. Biogas involves application of nanotechnology to improve biogas production. The controlled introduction of iron oxide nanoparticles in organic waste treatment can increase the production of biogas up to 3 times. Iron oxide nanoparticles feed the bacteria and enhances the biological efficiency. Very thank you. Now my discussion on this topic is over. Now the session is open for discussion. Actually, I want to talk a lot more, but I am very sorry because I am suffering from cold and cough today. But since I promise Dr. Sudhakar Bonde. That's why I am here. Now this topic is open for discussion. There are a lot of eminent persons. They can guide us. They can discuss issues because we have a lot of problem in synthesis and characterizations because in Jalgaon city, Jalgaon University, we don't have any facility. Hello? Hello? तो screen कसा आहे तो?
Go ahead, sir. Go ahead.
Yeah, go ahead. You are audible, sir.
Just a minute. Just a minute.
Now my discussion is over. The topic is open for discussion. Hello.
हाँ सर एक मिनट मैं बोलता हूँ.
Sir, now the topic is open for discussion.
Yeah, anybody can unmute themselves and raise their hand and ask a question, please.
So now it is a question answer session. So please you can type in chat box also or you can unmute yourself also.
Hello, this is
Yes,
Ravi.
sir. Good evening, sir. This is Saluraj from Krishnapalli. There is an excellent presentation on nano materials. I enjoyed your presentation. Thank you so much. And I have a question, sir. Who is a
Yes,
pioneer
yes.
in the world, sir, in nano materials?
Hello.
Who is pioneer in the nano materials area in world nanotechnology?
Payman, Mr. Payman.
Are you able to hear?
Yes.
Yeah,
Okay.
he's asking who is the pioneer in nanotechnology.
Yeah.
Payman.
Who is the leader in technology, nanotechnology? The nano materials. Who is the leader in the world now? Who is in the advanced stage?
I don't know exactly because a lot of people are working. Who is the leader?
Okay. Leader, yeah. Technology-wise, who is in the forefront? That's what I'm asking. And where are we? Indians, where are we?
Sir, there are a lot of people working on the nanotechnology and different applications. Therefore, we can't say one name. Okay.
Oh.
A lot of people are working.
Okay, sir. Just that electric cars and this Tesla is the leader. Like that I'm asking. Any country, any Western countries are leading like that.
Yeah.
Okay, sir. Thank you. It was a very good presentation. Thank you. I enjoyed your presentation. Thank you.
Thank you, sir.
This is
So
Ravi
anybody
calling from Canada.
audience?
Can I speak?
Yes, sir.
Thank you, Dr. Professor Rajendra Vogalade. It was a
Yes, sir.
very engaging presentation and you covered the entire wide spectrum of nanomaterials. I think we are really very grateful. It was a very engaging presentation. Just as a comment, in our research group, we have been working on aluminum alloys and magnesium alloys, particularly for lightweighting in the auto industry, and also for electric vehicles. And we are trying to develop nano composites that you mentioned in magnesium-based alloys and aluminum-based alloys. We've been using ball mills to really produce nanoparticles and some microparticles of alumina, magnesium boride, etc., essentially to improve the mechanical properties of magnesium alloys to produce composites. One problem is quite often these particles, tend to agglomerate.
Yes, sir.
And the homogeneous distribution of these particles, unagglomerated particles, is essential because we are using a variety of techniques like using sonotrodes in the melt as we add. So this is a comment. So agglomeration is a problem. Quite often, we use other techniques to enable the distribution in the liquid or semi-solid metal as it solidifies, so that we get a good homogeneous property of the entire material. Just a comment. That's one problem we have right now.
Sir, one thing is, when a material becomes a nano, its reactivity is more. It is not stable. And that's why it gets agglomerated.
Mhm.
it is very difficult to have nano materials, okay, because its reactivity increases at nano scale, and therefore it gets agglomerated.
You got
During our,
your point is very well taken. Thank you. That's a very good observation.
yes, sir. Yes,
I will take 1 minute
yes, sir.
for the benefit of the members. I'd like to tell you, Professor Ravi is a past president of ASM International, USA, and he is a very well supporter of ASM International India chapter. So I will request him to bless this material advantage chapter. Professor Ravi, please.
Yes, sir. Materials advantage, though it's composed of 5 different societies, it is a very good start for our students. And many of these students, eventually when they graduate, they diffuse into ASM as professional members. And for the students, I would very directly say you have made a very good decision to join the Materials Advantage chapter. And obviously your chapter is very active right now. I can see that from this meeting itself, its participation, along with a very important professional chapter in India, the India chapter. And by associating and also get involved with your professional chapter also through your representatives, and also get good contacts so that they will give you a lot of insights to how to transition into the professional careers or join the academia. All these opportunities are there. Congratulations. This is a great opportunity. Wish you the very best. Thank you.
Thank you, Professor Ravi.
Thank you, sir. Thank you. So any question from anyone?
Hello. Sudhakar Mote sir, we are
Hi.
trying to establish a MOU with Material Science Department of Kavaitri Bhanabai Chaudhary Uttar Master Vidyapith. And through that MOU, we are going to conduct a different workshops and different seminars, because we have MSc in Material Science at KBC NMU, and I am a research student of KBC NMU. Therefore, I think there is no problem of establishing a MOU with university. And as you have already told, you have established a MSc Material Science with our organization in Bombay University. Similarly, we will try in Jalgaon University also.
Okay, thank you.
We
Let us
require
discuss
only your support.
deliberate. Yeah, our professional support will be always there. That is not the
Yes,
big
yes,
deal.
yes. Thank you, sir.
So, sir, anybody having any questions? Okay, as there is no question in chat box also, and so I will move towards the next step in your webinars. So thank you very much, Dr. Rajendra Vagude sir, for introducing us to the world of nanomaterials and the ancient and medicinal use of nanomaterials and nanotechnology. Now now I realize that this nanomaterial will definitely going to a part of our routine life. So thank you very much, sir, for introducing to this world of nanomaterials. Now I will move towards the last session of the meeting, that is towards the vote of thanks. So now I would request Mr. Sandeep Rege sir, Secretary of ASM International India Chapter, to sum up the session. Over to you, sir. Sandeep Rege.
Sandeep, 1 minute. I'll request
Yeah.
Professor Dusane to summarize the thing. Professor
Okay, sir.
Dusane, please.
Okay, sir.
Yeah, sure. Good evening to all of
IIT
you.
Bombay.
Yeah, yeah. Good evening to all of you. As I think I wrote in the chat already, my introduction, Professor Rajiv Dusane, working in the Department of Metallurgical Engineering and Material Science at IIT Bombay. Nice presentation in terms of giving a broad overview of what nanomaterials can do. Definitely, I also wrote in the chat box that such presentations are important in terms of generating curiosity in the minds of young students. However, equally important is to realize that just getting curious is nothing, not the end of the story. Fundamental physics is behind what we see in nanomaterials today. And that fundamental physics has to be understood and appreciated. And for this, such components have to be incorporated in our course curricula. And if the existing faculty, I understand the status of all our universities and colleges across the country. Though I'm very delighted to say that colleges in Maharashtra are much more equipped in terms of faculty who can handle such fundamental issues. However, there are enough people who have, either superannuated or would like to engage with these students in terms of imparting the basic aspects of this, so-called, this word nanotechnology is very attractive and misleading and dangerous. Students get attracted, if you recall, astrophysics is another one. It is very attractive. Earlier, when quantum started, it was a similar thing. But the world has developed to a large extent, and it is only on the basis of understanding the fundamental aspects of these materials. Characterization of these materials is another issue, because when you work on the nanoscale, you do not know whether you are looking at your material or whether there is something sitting adjoining to your material that is being viewed by the instrument. Instrument capabilities, understanding instrument capabilities in terms of its limitations also, what an instrument can do, what it cannot do. Understanding transmission electron microscopy, understanding scanning electron microscopy, in terms of getting true knowledge about the material. And see, for example, students many times even do not know whether determining the structure of a material is equivalent to determining its property. So the structure property relationships have to be established in fundamental way. And therefore, it is a huge task for even the faculty members. IIT Bombay has initiated training for teachers. There are a month workshops where faculty can come understand certain aspects. But my reservation against many of these things is that unless and until the students get an hands-on, teaching SEM, TEM from a textbook is really, it is just giving an introduction, but a student can never work on a nanomaterial if he doesn't go and to an institution where he gets to at least see how a TEM looks like. So therefore, it is important because it would not be possible for every college to have a TEM. Even institutions like IIT Bombay got TMs after so many years because there are mammoths to maintain, very expensive equipment. But today it is possible through the various projects. You can write sub projects and get small fundings for visits of the students. All this is possible, and that is what should be emphasized, because unless and until the students appreciate all these aspects from fundamental point of view, no new things can be given, can be done. It will always be otherwise, doing small things here and there, not having a big impact. So therefore, it is important that the nano material aspect is understood and appreciated from fundamental point of view. Quantum mechanics, interaction of light with matter, how the interaction changes as a function of size. What are electronic excitations? What are molecular excitations? How do these molecular excitations change when molecules become small? And therefore, all these things are important, and more emphasis has to be given first. You people run courses in MSc. So MSc first year should emphasize more on these aspects. Teaching physics with or keeping in mind the implications of the physics aspects towards material science development is key. And therefore, physics teaching has to change a lot. We have to keep in mind where the fundamental principles of physics lead to development of materials and technology. And that connection has to be mentioned. Not easy to do, easy to say, but not easy to do. But somehow we have to start at some point, because only then we can reach or even utter the word technology. Till that time, we can only teach what goes in technology, but trying to not to access, but trying to initiate new technologies, we need to have fundamental understanding how these fundamental aspects lead to the development of new technology. So with that suggestion, I think I would like to again congratulate all those involved in initiating such activities in form of that materials chapter. Good initiation. Students would get an opportunity to interact. We have put our information as far as mobile number and address is concerned. I welcome all the students, whoever would like to talk to me in connection with his aspirations to work in these materials. We have a lot of infrastructure with us. I work in silicon nanostructures for batteries, silicon nanostructures for thermoelectric generation. Solar cell is my basic area of expertise. Have been working in solar cells, thin film solar cells for the last 30 years. So, student, I urge the students to seek, avenues where they would get an opportunity to go beyond what is being or what is available in their institutions. So, with that, I would like to thank Dr. Bonde and all. Normally, this time one tries to forget if there is any engagement, because evening, Saturday, Sunday evening, after the whole day, still because of this online webinars, Saturday, Sundays are no more Saturday, Sundays. You can always have uh, a seminar or a webinar even, but that is an advantage of having all these webinars. So something has
Thank you,
come.
Professor Dusane.
Yeah.
Now, may I have somebody from the North Maharashtra University? Any research scholar or any professor? NMU Jalgaon? I am seeing a lot of doctors. Saroj Bhole, Vijay Kumar. Anyway, thank you. Thank you very much. Sandeep, please. Sandeep, you can go ahead.
See, after very nice talk of Dr. Vahulde and summarized by Dr. Dusane, this is vote of thanks by Sandeep, myself from India chapter. We first of all thank Godavari Foundation and the Godavari College of Engineering and Polytechnic Jalgaon for allowing us to have a material advantage student chapter there. Also, I would like to thank Dr. Rajendra Vaguldeji, Dr. V.H. Patil, Principal, Professor Yogesh Vanjari, Professor Kodi, for having such a nice nanomaterials synthesis and its applications. It was very nice of you to have a basic, though it is a very basic lecture, as you talked about in the beginning, but it turned out to be a very nice and very important and very informative lecture. And as rightly spoken by Dr. Dusane, it has created a lot of lot of things in the minds of participants here. You talked about nanomaterials, the size of nanomaterials. It's the right from volcanic ash, shoot from forest fire. Also, you talked about liposome, carbon nanotubes, graphene, their usages. You also talked about the classification of nanomaterials like 0 dimension, 1 dimension, 2 dimension, 3 dimension nanomaterials. Then the isotropic, anisotropic. Also, you spoke about the synthesis of nanomaterials from how you did it with hydrothermal for nanorods, nano flowers of Fe2O3 with some polymers, and it can help industry in great ways. Also, you talked about the nanotechnology introduced in 1959. Its usage in physical, mechanical, optical, and electrical properties, improving the electrical properties. Also, you talked about the nanomaterials in green energy, like nano in green energy, which so nano in solar cells, quantum dot solar cells, GML, that's gradient multi-layer nanofilms, bioenergy, into biomass, nano catalyst. So it was from the nano material introduction towards even the application and the synthesis. So it was very nice of you to have a nice introductory lecture, but this will also help a lot of participants to create a lot of enthusiasm for nanomaterial. And thank you very much for the whole engineering college and the students there who have participated in this lecture, introductory lecture. And we are hoping to see these so many lectures coming up from Godavari Engineering College. And we will have these regularly lectures, maybe once in month or maybe twice a month as we go forward. So thank you very much. Thank you very much, all the participants. And I would like to specially thanks Dr. Ravi Ravindran, who has joined us from Canada. And he is very supportive of this SM International India chapter. And very nice of you, Doctor, to have joined us and helped us in many ways. So thank you very much. Thank you very much, Dr. Dusani, from joining from IIT Bombay. And thank you very much, all the participants. Thanks once again, Dr. Rajendra Vakuldeji, for your nice
I just
lecture.
want to make a
So
comment.
thanks. Yeah.
Only one
Please, sir.
sentences. I would.
Yeah, sure, sir.
The trend is right now to have if there are MA chapters within the region of a professional chapter, such as India chapter, Sudhakarji, you may kindly consider having the chair or his delegate of the MA chapter on your council, the executive committee of your chapter, so that there's a students directly participate, and you have direct communication with the students. And we are implementing it, starting to implement this in Canada. So kindly consider. Thank you.
Yeah, nice thoughts, sir. We will definitely look at it, and we will work out some ways to do that.
Now,
So
already
thank you
we
very
have
much.
2 nominations from the MA chapter to our executive committee, just for your information.
Yeah, good news for India is that the Indian students have made a history. Sudhakarji knows we have one lady student, a PhD student from Kanpur, has broken the ceiling. She's the first and also lady member of the board of trustees of ASM International, the first student outside North America. Thank you.
Oh,
Jalgaon people also can have that. Jalgaon people also can opt for that.
Exactly. They need not be from IITs, can be from colleges as well, so long as they are members of
yeah.
AIM.
Right, sir. Right, sir.
Okay.
Thank you. Thank you
Okay,
very
yeah.
much,
Thank you.
Dusani ji.
Yeah. Thank you so much. Yeah. My pleasure.
Thank you, sir.
Tomorrow we'll be celebrating Platinum Independence Day. So all my best wishes to everybody.
Thank you. Same to you.
Thank you. And I request this Jalgaon chapter, MA chapter members to take benefit of our regular series of lecture of the main chapter also. We'll send you the invitations also there, and then you can coordinate with us. Thank
Yes,
you.
sir. Definitely, sir. Definitely,
Thank
sir.
you.
Thank you.
Okay, bye.
Thank you.